Okay, hopefully this is working. And it's recording, right? Yeah, okay, great. Let's flip this. Okay, so I guess I'll start off with some announcements as people roll in still. I don't know if anyone else is going to come in. So a few things. First is going to be homework, right? It's due on Tuesday. I know that's in the middle of like Rosh Hashanah. So for those that like might have a conflict with homework, email me. I'm thinking if you can turn it in early, that's great. This isn't like a hard homework like at all. But if you like really can't, we'll work something out. But just let me know. And so that's homework. What else? Piazza. Second thing. So yeah, Piazza is the extra credit mechanism in this class for my recitations at least. If you so there's about 65 people that are registered currently, and a handful of those people like aren't in my recitations anyways. And I have 80 kids. So that means there are like 20 or so of you guys that haven't registered for Piazza yet. So get on that if you haven't already. I mean, it's free points at the end of the semester, so why not take them? There's been a few questions posted on Piazza already, and the average response time is 4 minutes so far. So I think I'm doing a good job. Let's see, what else? Office hours up there on the board. So I have them today, 1:30 to 3 p.m., and on Monday as well, 1:30 to 3 p.m. And they will be in 3W8 directions are on my website. You can find them there. And cool. Any questions? Yeah.
Yeah, saying for because of Rosh Hashanah, could I turn in my homework like to you physically now?
Yeah. I'll take it now. Yeah. Just turn it to me after class. That's fine.
Sounds good.
Yeah. Any other questions? All right, great. So I'm going to warn you guys, this recitation is going to be super duper boring because all we're going to do is cover definitions and like properties and stuff. And so because it's super boring, I brought a pillow if anyone wants to sleep. Just let me know. I'll put it right here. It's clean, I promise. So if you want the pillow, just grab it. I won't be offended if you fall asleep at all because I'm having trouble staying awake talking about this stuff. So, okay, where's my pen? Let's get started. So what are we doing in recitation this week? We're going to cover, again, definitions. And we're going to start with section 2.2, which is matrix algebra. And what goes on in this section? Well, we talk about matrix multiplication first. But to motivate the idea of matrix multiplication, let's talk about row and column vectors. So let's talk about row vectors initially. What are row vectors? They're going to be a matrix that looks like this, where you have one row and you have n columns. And let's say they're going to have the entries, who cares, x1, x2, blah, all the way up to xn. All right? And so that's going to be a row vector. And again, this is a 1 by n matrix, where we read 1 as the number of rows and n as the number of columns. And so it's kind of counterintuitive, right? Because if you play like chess or if you like read grids, you usually go like column and then row, but we're doing the opposite. Oh well, gotta deal with it. Second one then is going to be the column vector. And so you guys can probably guess what that looks like. Column vector is going to be let's say y1, y2, all the way through yn, and then we have n number of rows and just one column. All right, and this is going to be n by 1. Okay, and now that we've got row and column vectors, let's motivate the dot product. So what is the dot product? Well, in 114 or multi, we saw the dot product as, we took like, let's do it for like a 3 by 3 vector, or a vector with 3 entries. We took, I don't know, x1, y1, z1, x2, y2, z2. And when we dotted them, we got the answer x1, x2 plus y1, y2 plus z1, z2. So that was our 114 definition with those kinds of vectors. So now, how are we going to do the dot product here? We're going to take 1 by 3 matrix, so x1, y1, z1, and we're going to multiply it with a 3 by 1 matrix, x2, y2, z2. And you'll notice, right, this is 1, let's not do that. This is a 1 by 3. This is a 3 by 1. And then our result then should be 1 by 1 by what we do in matrix multiplication. And yeah, that's exactly what we get, because we get the x1, x2 plus y1, y2 plus z1, z2, right? And this is a number, right? That's going to be a scalar number. And so, yeah, that's what the dot product is now. Okay. So now that we have the dot product and row vectors and column vectors, let's motivate then multiplication. So what do we have then with matrix multiplication? Well, if I'm given a matrix, here's A, here's B, and here's AB. And okay, so what now? So let's give some dimensions to these matrices. So A we'll do n by n, and then for B we'll do n by p. And what would AB be, the dimensions?
N by P.
Yeah, m by p. Yeah, m by p. Okay, so yeah, so as you notice, then and that dimension there, those n's, they have to be equivalent in order for this to work. And what really is going on when we're doing matrix multiplication? Well, if I take, let's say, this row here, this is the first row, right? That's row 1, and then I multiply it by column 1, right? I'm going to get a dot product, right? We literally just talked about what a dot product is. It's a row and a column. So I'm going to get a dot product. That means I'm going to get a scalar, and that scalar is going to be up here, C11, which indicates that, oh, that's going to be like, I don't know, the entry of the row 1 dotted with column 1. Okay? And then in general, if I take the ith row and the jth column, just do that. So if I take the ith row and the jth column, then I'll have some entry, I don't know, in the ith row, jth column, which is like Cij, where this is the ith row, and here's going to be the jth column. Okay? And so, sorry. Matrix multiplication then is just, we're just doing a bunch of dot products over and over and over. Cool. Any questions? So let's talk about some properties. Properties of matrix multiplication. What are they? First one is going to be associative. So what is that? AB times C is going to be A times BC. So if I have 3 matrices, I multiply AB first and then multiply C. It doesn't matter if I did BC first and then took A on the left. Where your matrices are is very important, but the order that you multiply them in doesn't really matter. Okay, so it's associative. What else? It's left distributive over addition. And so what does that mean? That means that A times B plus C is going to be AB plus AC. And then it's also going to be right distributive over addition. which means that A plus B C is equal to AC plus BC. Okay, so those are fairly standard. Those seem fairly intuitive. The one that isn't, that it initially isn't too clear, but it becomes really clear immediately, is that it's not necessarily commutative. So in general, AB does not equal BA. There are cases where this will be true, but you're usually safe to assume that this is not true. And of course, we'll talk about cases when they are true. And one of them we'll talk about immediately right after this, the Dany Matrix. The other one then is when you... So if it's not the identity matrix, it's going to be a coincidence. And it's because then one of the matrices is in the center of the other matrix. Don't worry about that term. We won't get to it. Okay? And again, you can see this, again, by a dimensionality argument. Just assign random dimensions, and they won't match up. Okay. So now let's talk about the identity matrix. Ooh, actually, before we jump to identity matrix, I want to talk about something real quick. So this is what I skipped in the last recitation. I was like, I have so much time remaining. So there's a really useful, there's an important type of matrix multiplication. Well, I don't know if it's type. It's more like a circumstance. So you'll get the following scenario that goes on. You'll have like A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so that's just, your standard 3x3 matrix. Those like A11s, just think of them as like some random numbers that I just didn't want to write out. Okay? And let's say B is equal to 1, 0, 0. What is AB? Actually, don't even give me the entries of AB. Just tell me what AB is. The first column. Why do you think that's how do you know it's the first column? Oh, if you multiply it out, you get the first column, right? Right. So if you multiply it out, right, when you do these dot products, these zeros like kill these guys, and then they kill like these guys, right? And so yeah, so when you see B equals something like this, you should immediately think it's the first column because I only have an entry in the first entry of B. Okay, so this is going to be the first column, A11, A21, A31. All right. So that's because B is there. Okay, what if B? Okay, what if B is equal to 0, 0, 1? Yeah, I get the third column of the matrix. So then AB is going to be A13, A23, A33. Okay. What if B is equal to 0, negative 7, 0? Yeah, exactly. Now I get the second column times negative 7, and that's going to be negative 7, A12, negative 7, A22, negative 7, A32, right? So the idea then I want you guys to see is that, okay, when you have this special 3 by 3 times 3 by 1, you have some types of multiplication where you just simply extract rows of the matrices as your result. And we'll see this a lot come chapter 7 when we deal with eigenvectors, is that, I'm just going to write B equals that, and I'm just immediately going to give the result, and you guys are going to have to know why, and it's because of this. I mean, now that you guys have seen it, once you see it again, it should be pretty simple. Okay? And the other thing then is, so it's fairly obvious when I just say B is like a column vector, right? When B is a column vector like that it's immediately clear that's true. What if I do the case then where, let's write over here, what if B is equal to 1, 0, 0, and then some random garbo? All right, so what if B is a 3 by 3 matrix, right? But I know the first column is 1, 0, 0. So what is AB? All right. What can you at least tell me about AB?
The first column.
Yeah, you can tell me what the first column of AB is, right? And what is going to be the first column of AB? Just first column A. Yeah. And then who cares? That's not the point of this exercise. I don't care about what the other entries is. I just want you guys to see that, hey, look, as long as one of these guys is in a column of the B matrix that you're multiplying by, right, I'm going to be able to just simply extract one of the rows, one of the columns from A. Okay, cool with that? All right. So now then, let's move on to the identity matrix. All right, and so it has to be square. So it has to be square. And then how do we denote the identity matrix? Well, I'm gonna write. It's usually I just write as I, and then since it's square, I only need to give one of the dimensions, right? Because if I know one side, I know the other side. So let's write IN, and I'm gonna section this guy off from the other guys. Okay, and what does the identity matrix look like? Well, it looks like the following. So examples then, let's say I2, right? It's 1, 0, 0, 1, and then I4 is 1, 1, 1, 1, and then I do this a lot. Not sure if it's allowed on the exams, but I just put like big fat zeros here. To indicate that those entries are all zeros. I don't want to write 0 like a bunch of times, so we'll just leave it like that. Okay, and so the 1s then go on the main diagonal of a square matrix, okay? And so the main diagonal of a square matrix is going to be from the top left to the bottom right, and that's literally the only diagonal that we're ever going to care about in this class, all right? We will care about like the one diagonal like right above it like later on, but like just for now, for the first half of this class, just like we don't care, okay? We don't care about any other diagonal. That's the only diagonal. When I say diagonal, that's what I mean. Okay? So yeah, okay, so that's what the identity matrix looks like. Cool. What does it do? Well, if A is square, then it's commutative with A. And what does that result in? What is A times identity matrix? And this is actually a really cool application of what we did up here. Yeah, you get itself, right? And why is that? Let's think. What is the identity matrix, right? The first column of the identity matrix is going to be 1, 0, 0, 0, 0, 0, right? What does that do? It extracts the first column of A. All right. The second column of the identity matrix is going to be 0, 1, 0, 0, right? And what does that do? Extracts the second column of A, right? And then, okay, then like the last column of the identity matrix is going to be all 0 and then 1, right? And that's going to extract the last column of A. And then once you've done all that, you just get back A, right? Because you extracted every column every time. Okay, so that's why. And in general, AI is equal to A, or IA is equal to A, depending on dimensions. again, I mean, you have to make dimensions work, but if you have an identity matrix, you'll be able to make it work. Okay. Any questions about an identity matrix? All right. Yeah, it's fairly common. It's fairly easy to get the hang of that. Where am I? Okay. Let's talk about transpose. All right. So what is the transpose? It's best to demonstrate this with an example. So I have 1, 2, 3, 4, 5, 6. Then A transpose is equal to 1, 2, 3, 4, 5, 6. And what did I do? This row becomes this column, and then the second row becomes the second column. Okay, and this is a decent example because we see that my dimensions here are 2 by 3, and so when you transpose a matrix, the dimensions switch right here. Now it becomes 3 by 2. And so for square matrices, like whatever, right, the dimensions aren't going to matter, but we can use dimensionality as an argument then later on in some properties. So the first one is A transpose. All right, and then I'm going to take its transpose. So what should I get? A, right? Yeah. And that's exactly what I get. And to see this, I mean, it shouldn't be too hard to see, right? So here's A transpose. And if I take this first row and I make it my first column, well, that's 1, 4. And then if I take the second row and make it my second column, that's 2, 5. And it's like, hey, that guy looks like this guy, right? So A transpose equal to A. Number 2, so A plus C transpose. Under addition, it's going to be distributive. All right, so A plus C transpose is going to be A transpose plus C transpose. And then the last one is the one that you're actually going to have to like write on a cheat sheet or like make a conscious effort to remember. But A times B transpose is going to be B transpose times A transpose. And the reason is just make any sort of dimensionality argument you want. So if I let A equal, I don't know, 2 by 7, and B equals 7 by 4, right? This result is going to be 2 by 4. And then if I take the transpose, I'm going to get a 4 by 2. Okay? Well, what is B transpose? B transpose is 4 by 7. A transpose is 7 by 2. And hey, these dimensions actually match up. All right? If you did A transpose, B transpose, those dimensions won't add up or won't match. And so, yeah, and then I get a 4 by 2, right? So don't be baited by that. If it's a square matrix, this holds in general. So usually it'll come up in the context of square matrices, and then you'll do A transpose times B transpose on accident, and then you're going to be like, oh, I'm an idiot. So keep that in mind. Okay. Well, that's the transpose. Let's talk about upper and lower triangular. So this will be a really quick section. Upper triangular. What do these matrices look like? Well, so you have your main diagonal. All right, and upper triangular just means that everything below the main diagonal is 0. All right, or the way you can think of it is you only have entries in your upper. You only have non-zero entries in your upper triangle of the matrix, right? So you can kind of see that there's like a triangle here, right? Kind of. So that's what upper triangular matrix looks like. So for example, then you can have, oh, I don't know, the identity matrix is going to be upper triangular, right? Because again, all we care about is that these guys down here are 0. You can have something like 1, 7, 4, 0, negative 3, 0, 0, 0, 0, right? Again, this is upper triangular because these 3 entries down here are 0, and then, heck, even the 0 matrix is going to be upper triangular because we only care about entries below the diagonal being 0. So then lower triangular, you can probably guess what this means. You have your main diagonal, and then now you want the entries up here to be 0. So what is that? Well, hey, the identity matrix, it works again. So that's a neat true-false question right there. Can a matrix be simultaneously upper and lower triangular? Why not, right? What else? Then you have, I don't know, 1, 0, 0, 0, 0, 0, 4, 7, 0, right? That's upper triangular, or that's lower triangular, and then I guess the 0 matrix is also lower triangular as well because the upper entry is 0. Okay? And if it's simultaneously upper and lower triangular, then it's going to be a diagonal matrix. So it's both upper and lower triangular. And so what do these guys look like? I mean, the identity matrix is diagonal, right? Because you literally only have entries along the diagonal. So you'll have something like 7, 4, 0, 6, negative 1. And then everything else has to be 0. I'm not going to fill that out. And then big fat 0 down there. All right, so those are like diagonal matrices. Yeah, so diagonal just means these guys are 0 and these guys are 0. Okay. So why do we learn about these? Well, lower triangular times lower triangular gets you a lower triangular matrix. Upper triangular times an upper triangular gets you an upper triangular matrix. And the diagonal times the diagonal gets you a diagonal matrix. All right, and so these will just help with computation. You can just throw in a bunch of zeros because you know that it has to be true. Okay, any questions? Hey, guess what? We finally made it out of one section. So now we can move on then to 2.3, which are linear systems. And so, okay. So what are linear systems? I think I'd cover this in this class, so I can do this pretty quickly. If we're given a system of equations, and this is just going to be random numbers. So 7x1 minus 3x2 plus 4x3 is equal to 5. Negative x1 minus 2x2 plus 3x3 is equal to negative 4. And then 2x1 plus 5x2 minus x3 is equal to, 7. Okay. Remember how we throw this then into a matrix or into matrices. So we take the first row, and that's my first row. Take the coefficients. So you get 7, negative 3, 4. And the second row, you get negative 1, negative 2, 3. And then you get 2, 5, negative 1. Okay, so you just take the coefficients from each row. This matrix is going to be called the A matrix. You'll then have a vector of unknowns. And so what are my unknowns in this equation?
X1, X2, X3.
Yeah, x1, x2, x3. You can call them x, y, z. But the reason why I'm calling them x1, x2, x3 is because this is going to be the x vector. And so I didn't want to confuse you guys with multiple x's, or like two just x's instead of having subscripts. And then here you get the right-hand side, which is 5, negative 4, 7. And this is equal to b. All right, so you get this ax is equal to b form, which is called the vector formulation. Vector formulation. And A then is going to be a matrix of coefficients. X is going to be a vector of unknowns. And B is going to be whatever is on the other side of equals. Okay. And again, if you multiply these guys out on the left-hand side, you should get exactly those three equations. Okay. So now then, let's talk about some terms. Homogeneous. All right. Not homogeneous, because homogeneous describes milk. And we're talking about system of equations here. All right. So homogeneous systems of equations. What are they? Well, it's b equals 0. So b is the 0 vector is going to be a homogeneous system. And in the spirit of last class then, let's talk about the geometric interpretation. What are some interesting things about a homogeneous system of equations? Well, let's think. Do I know my points are going to intersect? Or will this system have it? Will every homogeneous system have at least one solution? One common solution?
Yes.
Seems to nods. Okay. What is it?
Sir.
The origin. Okay. So then every maybe that's not the way to phrase it. So there is. I'm just going to write it with a backwards e. There exists at least one common intersection point. And we know there exists at least one because it's at the origin, right? So let's think about that then. In R2, what does that look like? Well, that means when I have a system in R2, right, I have lines. And where do those lines have to intersect, at least? At the origin, right? So I can have lines that look like this. Right? They intersect at the origin. What's another way my lines can intersect? Remember, there are two ways for lines in R2.
Same way.
Yeah, they can be the same line. So then I can just have this be the same line. So we have two intersections. So we have two ways of intersection, right? For two lines in R2, you have the two lines that intersect at a point, or you got the same line, and they have to run through the origin for a homogeneous system. Okay, so that's the geometric interpretation of homogeneous. So now, if we have inhomogeneous or non-homogeneous, I say inhomogeneous. I'm not even sure if that's a word. But whatever. So this is the case then where b is not equal to 0. So just like this vector, this up here, that's an inhomogeneous system of equations. And so what's a geometric interpretation of this? Well, okay, so let's think about it. Am I guaranteed a common intersection like I was before?
Yes.
Okay, someone says yes, where?
At that. It depends on like what B is.
Depends on what B is. Well, I mean, so does every system have a solution? Or does, right, so let's just think, does every system of equations have a solution? Not necessarily, right? Because if you have 3 planes, right, they might not intersect at the same point, okay? But if I knew that it was a homogeneous system, then I knew that they all had to run through the origin at some point, right? Here, they might not run through the origin, right? In fact, can I have a solution at the origin for an inhomogeneous system? No, why not?
They all have to be 0.
Yeah, so let's think about this, right? What is a solution to a homogeneous system? If the solution is the origin, right, then this vector of x's is going to be 0. What is that going to do when I multiply everything out?
Make B 0.
Yeah, it's just going to kill everything, right? It's just going to make b 0. And so when I have an inhomogeneous system, I can never intersect at the origin, all right? So there may not exist... all right, so there may not exist a solution. And if there were a solution, it can't be the origin. So if exists, maybe I shouldn't say solution because we're doing geometric interpretations. I should say may not exist a common intersection. And if there exists, so backwards E, there exists a common intersection, cannot be the origin. Yeah.
Wait, B has to be a point, or it can be a line, or
B is a vector, right? But so it has to be a point.
it can be a system of like.
Well, when we
depends on T, right?
right, but then X will be a line,
Oh, okay.
right? B will always just be a point.
Okay.
Yeah, B will always be just scalars. Right. So again, so for inhomogeneous systems then, all right, if they intersect, so first of all, they may not intersect at a common place, right? Think, I don't know, this iPad and its stand, right? I got 3 planes. This back plane, the iPad, and then this plane on the bottom, right? There's no common intersection here, okay? And but if they did intersect on a common place, and I knew it was an inhomogeneous system, that intersection cannot run through the origin, whether it be a line, a plane, or a point, all right? Just can't be the origin for inhomogeneous systems. Okay. And there's a reason why we're distinguishing this, because when you hear the word homogeneous, it's going to come up over and over and over again throughout the semester. It always means that like there is a solution at the origin. That's what homogeneous like means, that there's going to be a solution at the origin. So when we get into differential equations, we'll see this again. Okay. Now let's talk about consistent and inconsistent. So consistent just means that there exists at least one solution. I mean, the geometric interpretation is fairly obvious then. It just means there exists at least one common intersection. Right? So they intersect at least a point. They're not going to miss each other. So if we say we have a consistent system, we have a solution. So a lot of problems then will be like, prove that the system is consistent. And so all you have to do is, well, you can find a solution that proves that it's consistent. The other way you can do it then is you can make some rank argument, but we're not going to get to that. And I think you guys started talking about that in class. So. Inconsistent. All right, there does not exist, so that's the backwards E with a slash, a solution to the system. And again, geometrically, that means no common intersection. questions? All right. Let's see. So this is where we stopped on Wednesday, but we're going to go on because I have like 8 minutes. So let's go and go back up here, and let's look at this matrix right here, right? So you have a matrix A, and to solve system of equations, we always construct then the augmented matrix. And we call that, A pound A with the hashtag, A sharp, whatever. So what is this? Well, it's the matrix then where you put A, so you draw a line, you have A on one side, and then you have B on the other side. And so in our case then, this will be 7, -3, 4, -1, -2, 3, 2, 5, -1, 5, -4, 7. And to make consistency and inconsistent arguments, we use like the rank of A, and we use the rank of A, the augmented matrix. That's how we make consistent arguments. Again, I didn't even cover what rank is in this class, so don't worry about that for now. You don't need it for your homework. And then by performing row operations on this matrix is how we find our solutions to our system of equations, which you guys have seen in class already. So, okay, so that was that. Now let's move on to then elementary row operations, or 2.4, which is row reduction. Yeah, okay. And let's just then talk about the elementary row operations. So for now, since I'm not talking about row operations in the context of system of equations, we're just going to be talking about row operations on a 3x3 matrix. Don't worry about the interpretation of it, the geometric interpretation for now. But let's just talk about then, what are my 3 elementary row operations I can perform? Someone give me one of them.
Scaling.
Yeah, sure. So multiply a row by a non-zero scalar. All right? So let's say I have a matrix. So let's just have our default matrix. Let's put it up here. What should it be? I don't know. 2, -1, 4, 1, 0, -1, 4, 3, 7. All right, so that's just going to be the random matrix we're going to do. And then, so the tilde means that we did some row operation or multiple row operations. And let's just say I did 2 times row 2. All right, and what do I get? Well, I'll get 2, -1, 4, 2, 0, -2, 4, 3, 7. Okay, so I can multiply a row by a non-zero scalar. You can divide rows, right? That's just multiplying by a fraction. What else can you do? Yeah, so you can do that. Can't multiply by 0 because then you'll just zero out that row, and that kind of defeats the whole purpose. So don't multiply by 0. Okay, what's another row operation?
Permute.
Yeah, permute. All right, so you can switch rows. So let's say I can just permute the first and second row. 1, 0, -1, 2, -1, 4, and 4, 3, 7. So again, we're starting with that matrix always. And then the last one then is I can add a multiple of one row to another. So in this case, why don't we do, let's do row 3 is equal to row 3 minus 2 times row 1. Okay. And what does that get me? So row 1 stays the same, row 2 stays the same, And then row 3, I get 4 minus 2 times 2, so that's 0. I get 3 minus 2 times a negative 1, and so that's 5. And then I get 7 minus 2 times 4, which is negative 1. Okay. And on your homework, don't show this. Don't show this. Just have the tilde and the matrix. That's good enough. I can figure out what you did. So yeah, just try to keep it like neat. We don't need all these. You don't have to say what you did. Okay. So yeah, those are our 3 row operations. And now let's jump to then row echelon form. Which is REF. So the 3 conditions. The first condition is all rows of zeros are on the bottom. The second condition is all rows, all non-zero rows, 0 rows, must begin with a 1, and that's called the leading one. And then the third condition then is the leading one of a row must be to the right of the leading one in the row above. Rows above. Okay, so what are some examples? You got 0, 1, 0, 0, 0, 1, 0, 0, 0. That's an example. You can get 1, 2, 4, 3, 0, 0, 2. That can't be a 2. 0, 0, 1, 2. So those are examples. And then what's not an example, 1, 1, 3, 0, 0, 0, 0, 1, 2. Right? You got a row of zeros in the middle, and you can't have something like 0, 1, 7, 1, 2, 5, or 1, 2, 4, and then 0, 0, 1. Again, the second row violates it because this 1 isn't to the right of the one above. So, and then, so it's 950. So real quick, reduced row echelon form, RREF. 2 conditions. First condition is row echelon form, and the second condition then is any column with the leading one must have zeros elsewhere. So, for example, this guy we had above earlier, that's fine, right? Because every column with the leading one has zeros everywhere else. And then you can have something like 1, 0, 2, 0, 0, 1, 4, 7. That has to be 0. And then 0, 0, 0. This can be a 1 or a 0. It doesn't matter. Let's put 0 there. That's reduced row echelon form. So, okay. Yeah, so that's it then. I'm not going to get to the example of reducing, but that's fine. So next recitation, I think we're going to be solving systems. And I think I'm going to get to inverse matrices as well next recitation. So again, yeah, so announcements at the beginning of class where homework's due on Tuesday. Please sign up for the Piazza if you haven't already, because that's how you get extra credit. And yeah, and I had something else, whatever. Oh yeah, office hours today and Monday. So again, apologies for the boring recitation. Material was really slow at the beginning. I promise, once we get through this like matrix stuff, like this chapter essentially, like things will pick up a bit quicker, and these recitations will be like we'll actually do problems in these recitations rather than just talk about definitions and whatever. So, all right, have a good weekend. Take care, and I'll see you guys next week.
Have a good weekend.
Yep. Hey, yeah, thank you. Yeah, you're good. Yeah, I had someone else turn in their homework, so
Okay.
you're good.
Thanks, Evan.
Yep. Oh, thanks.
Are we supposed to hand in the homework right now, or?
No, it's due Tuesday.
Okay,
Yeah. I guess some people just want to hand it in early, so.
fair enough. I thought we handed it in class, not.
I'll take it early, like it's whatever, because I
Okay.
have to get them anyways.
Okay.
Eventually.
Thank you.
Yep.
Thanks.
Yep.